first even is number what? 12. So eventually just keep blowing and then it's going to start like moving.
Try to steal it.
Okay, that's right, right? It just sounds right. Number 12. Number 12. Can you guys see it? Final answer, the definite integral from 1 to 3 and 3 over x squared dx. That's enough time. What's the next one? 22. If you guys aren't ready, come on, let's go. Grade it. Section 4.3. Bridget. Distracting. 22. 0 to pi over 4 tangent of x dx. Next one. Remember, it's on the recorder if you need it.
28.
Nice. 60.
I did not get that.
Why not? Height was 6, base was 4, and 6 is 10. 10 times 6 is 60.
Where did it get?
Uh-oh. I don't know.
I wrote it right.
Right there. Number next one. 32 or 34? 32. Corey, focus. Why don't you? Come on, Corey. Number 32, 15. Number 34, a squared. Didn't we do this one together? Number next one. 46. Uh-oh, this one's a little bit of a longer one. A is 8, B is negative 12, C is negative 4, D is 30.
Good job.
Nice. Thanks, Benjamin. What's it? Just like nice. Number next one. 62. Oh my goodness, I have to scroll. That's annoying. I'm trying to work on it. I thought I could type with George's because he brought me one, but it didn't end up working. The trapezoidal on 62 is 11.7296. The trapezoidal on 62 is 11.7296, or I would say 11.730, right? Rounding to 3 decimal places. But the exact, hold on, you weren't supposed to know how to do this. Unless you used your calculator, then you could have gotten 12. What? So you could have used your calculator to find the exact. You didn't need to know how to do this part of it. This is section 4.3, no, sorry, section 4.4. So you guys, for this one to find exact, couldn't you put that in your calculator? And couldn't you get 12? Yes. That's how I expected you to do it on this one. Remember next one? Oh, we should see.
Don't let us.
Just give it to someone and steal theirs. Just kidding, don't do that. What's number next one?
86.
Are we close? Greater. Less. How are you supposed to visualize? Put little rectangles hitting at the left, hitting at the right. This one goes over the curve. This one goes under the curve. Greater than, less than. It was a how do you see it. Any more? 110. Oh my goodness. Okay. These ones were weird because they gave you funny information, right? Yeah. 110. The answer is C. How could you have done it? Can you graph X? Can you think about the area under X? What's the area under X look like? Triangle. And any area above, we make what kind of number? Positive number. And then over here, we're going to have area below, which we're going to make what?
Negative.
A negative number. So we're going to do this negative area plus this positive area. Something's turned on. I don't know what. I think it's this guy. So the final answer is this guy's a negative plus this guy's a positive, and the final answer is 36. Oh. to this guy, yeah. But I was doing the piece. So I was doing this area of x, and then kiddos, what would this area look like? What am I graphing? Nope. What am I graphing for the second integral? Straight line. What kind of straight line? Vertical or horizontal? Good. And what is this function if nobody's there? So I would graph it at y equals 1. And if I'm going from -3 to 6, who is that guy? A rectangle with a height of 1 and a base of 9, and it's all multiplied by 5. So 5 times 9 times 1, that's where they get this dude. And then this one, they did the positive triangle plus the negative triangle, and that's how they got the rest of the answer. What's wrong, Ange?
How do they know what the height? Oh, they just.
Because you have to plug in 6, right, to figure out this height. So then you would have to plug in 6 to x, which would be 6. You know that from 0 to 6, that's 6, right? And then over here you could plug in -3, so that'd be -3. And then this would be 3 again? 0 to 3. We could do -3, that's totally cool. We would have 1/2 base times height, but remember this needs to end up being a negative number because the area is below. Does that make sense? Cool. So we end up with 1/2 of 9 plus 1/2 of 36. 36 minus 9 is 27. And that's where they get the rest of the to solve. Answer is C. And then you guys said 112 also, right? Another multiple choicey one? Oops. Okay, and number 112 is right below. Final answer is C, 430. What did they give you on this one? Any clues? This is the problem. Did they give you a picture?
Yes, they give us a graph.
Okay, and
A table.
a table. What did the table say?
X and then x.
Were there any other directions besides the table and this little dude? Oh, come on, who wrote the directions? This is something you're supposed to write every single homework.
I wrote AP preparation.
That's a good name of it. What are the directions?
And 2 over 2 and 8, 7 tables. 2 and 3, 3, 5, 5, 8. Trapezoid approximation.
Trapezoid, that's what I was looking for. 2, 3, 5, and what was the other one?
8.
And that's it? That's all we got in the table?
Yeah, and then for y it's 8, 22, 27,
22, what was the next one?
7.
And what was the last one?
142.
Okay, kiddos, they gave you a table and they said trapezoids, using the subintervals as shown. So wait a minute. Subintervals. Here's what's going on. You're trying to approximate from 2 to 8, from 2 to 8 of a function. You know the heights at 2, at 3, at 5, and at 8. If they say use the subintervals, how many trapezoids am I making?
4.
No, 3. Trapezoid between 2 and 3, a trapezoid between 3 and 5, and a trapezoid between 5 and 8. Now kiddos, hold on. What's the formula for the area of a trapezoid? 1/2 base 1 times height 1 plus height 2. 1/2 divide by 2. Base 2 times height 1 plus height 2. You guys see the trapezoid formulas right here?
Yes.
Now where do they get the numbers? How'd they get the base of the first trapezoid? Change in x's. So Bridget, watch out, because the table, it looks funny. So, if they're doing the base for 1/2 base times height 1 plus height 2 for a trapezoid, from a table we get the base by subtracting the x's. So 3 minus 2 is 1 for the first trapezoid. A base of 1 times 1/2. Why are they choosing f of 2 and f of 3? Isn't that height 1 plus height 2? So, for the first trapezoid, we use the change in x's for the base, 3 minus 2, and we use height 1 plus height 2. We use each of those f of x values. So then for the second one, change of x is going to be the base. 5 minus 3 is the base. Height 1 plus height 2, f of 3 and f of 5, plus change in x for the base, height 1 plus height 2, f of 5, and f of 8. Does that make sense, guys? Then we just plug and chug from the table, and dun 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 dun, 430, C, dun dun. Cool? That's the end of our evens. That's on the video if you guys need to see it. And let's get, oh, no, let me go ahead and hit him. Notes! Let's get back to 4-4. Good news is we don't have to finish 4-4 today, but we do need to get some good work done. Well, that's good timing anyway. Go away. Thanks. Back to here. Thanks. And then let's get, I think he's okay. Here. All right. Let me quickly see if I can get my Bluetooth keyboard hooked up, because that would be awful nice. Is he on that? Let's test it. Maybe not that we're going to play right now. Yay! Okay. Here we go. Yesterday, I was doing all this craziness. Thanks, guys, for letting me test all that out. Okay. Shush. Bridget, you're still talking. Shush. Okay, yesterday, we did all this. What was I doing on all this page?
You were taking the words and putting them into.
I was taking the words and I was putting them into math. No question, kiddos. Just for me to connect the dots a little bit more, and one more time, you don't have to memorize this proof, hence why I didn't have you write it. All of this stuff, you guys were practicing on section 4.3 a lot more. Don't you guys notice the f of x values times delta x values? What do those look like that you guys were doing in 4.3? Well, yeah, but more specifically, don't those look like bases times heights?
Yeah.
F of x's are heights, delta x's are bases.
Yeah.
So all of those are adding bases and heights. Well, wait a minute, okay, of how many rectangles? Well, starting at 1 and going down to n. So n rectangles. What could n be? 3? Sure. 10? Sure. 100? Sure. 1,000? Sure. 1,000,000? Sure. So I am talking about the sum, because I'm adding them all together, right? Addition. From 1 to n. The sum from 1 to n. N rectangles, which could be 1, could be 10, could be 100, could be 1,000. Could be 1,000,000, could be 1,000,000,000. Now, when we add these up, do you guys notice that there's a positive f of x1 and a negative f of x1? They cancel out. A positive f of x2 and a negative f of x2, they're going to cancel out. Everybody is going to cancel out all the way down to the very end. He cancels out, but this guy remains. This guy remains. So we can do a sum of 10 rectangles and still get f of b minus f of a, or a sum of 100 rectangles, sum of 1,000,000 rectangles. So therefore, if I am trying to find the definite integral from a to b of f of x dx, all I need to do is take the limit as n goes to infinity of the left side, and the right side, the limit is just this constant, because the limit of any constant remains the same. So I can say the definite integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a. This is called the fundamental theorem of calculus because it puts together the idea of area, which is the definite integral from a to b of f of x dx. One big question in history that they were trying to answer. And the idea of an antiderivative. It puts together what we learned from section 4.1 to what we learned in section 4.2 to 4.3 and says, hey, they're all related. And so that brings us to what you guys wrote down, hopefully at the beginning of class, forever number 37, that says, if a function f is continuous on a closed interval a to b, then the definite integral from a to b of f of x dx is equal to, hold on, quick review, who is capital F?
Antiderivative.
Capital F is the antiderivative of who?
F of x.
Yeah.
Okay.
Add that into your forever card. We already have a forever card about what the definition is of an antiderivative, that capital F prime equals little f, or that the integral of f is equal to capital F of x plus c. We have to remember who this guy is. We have to find the antiderivative first. So even though the fundamental theorem of calculus tells me that this is how you solve the integral, the definite integral from a to b, the working definition, or description I should say, is this little part right here that says, ultimately by what I've shown, ready? It says find the antiderivative, and then realize you're going from A to B, which means, hey, plug in B, plug in A, and subtract. An infinite sum can be done with a single subtraction of an antiderivative. It's kind of crazy.
Yeah.
It's kind of cool. It's kind of crazy. And it's all proved once again using MVT. So, kiddos, how do we use it? Well, here we go. Don't we have an example to do? If the question says, find the area under the curve over the stated interval, it could also be said or stated, solve, another way of saying the directions, solve the definite integral. That's ultimately what we're doing. Solving it by hand, not using rectangles, not using trapezoids, not using n equals 4 or 10 or 100. Praise the Lord. 100, right? Some of you got tired with 3. Solve the definite integral by hand, doing the work the calculator was doing when it shaded and solved. Actually, it was doing a much more complicated process. Ours is easier because we are able to take a general idea, some general formulas, and apply them. We're able to take a problem, figure out what form it fits, and solve. That's what a computer has a very, very difficult time doing. Interesting. What do? We, number 1, find f of x, meaning the antiderivative. Number 2, we take f of x and we say, hey, we got to go from a to b. And then number 3, we actually solve by plugging in b and plugging in a.
Yeah.
Okay? So, antiderivative. Stink. Don't we want to rewrite this, guys? Okay. Keep the 1 to 4. He's important. We can't forget that. This is going to be x to what power since we're rewriting to solve? Negative 1.5, which would be negative 3 over 2. Does that make sense? It's in the denominator, negative exponent. Oh, my Algebra 1 kids are hating negative exponents right now. It's so sad. They're like, oh, if you don't get this now, you're going to be in trouble. Anyway, 3/2 because it's x to the 1 and x to the 1/2. So x to the 1.5. Like bases, you add the exponents. 1.5 is 3/2. Does that make sense? Now we got to go ahead and keep on going to antiderive. Technically, we're going to do negative 3/2 plus 1, which is plus 2 over 2, right? Help me out. Who is that? Negative 1/2. We can divide by negative 1/2, but ew, gross. Who likes that? Okay, that's cool. But otherwise, the rest of us might say, why don't we just multiply by the reciprocal? Is that okay? Okay, so we end up with x to the negative 1/2. Double check it. Can you bring down the negative 1/2? It cancels with the negative 2. Subtract 1, get negative 3/2 as the power. Perfect. Aren't we used to doing plus c? All right, let's keep that. That's okay. I'm going to go ahead and show notation by saying, hey, we're not done yet. We're solving a definite integral. We're supposed to get a numeric answer as long as we have everybody. Now, weird thing is, kiddos, look over here just for a second. Question, do you see a plus c in this expression?
No.
Oh, I just say the antiderivative, not the plus c. What's going on with that? Well, let me show you.
Bless you.
Bless you, bless you. Our next job is, well, hold on. I try to make things easier on your brains as much as possible. Can't we rewrite this as -2 over the square root of x plus c?
Yes.
Isn't that a little easier on our brains if we're going to plug in? Okay. So now, what does our formula say? We've done number 1, check. We've done number 2, rewriting it, check. Number 3 says, plug it in, plug it in. Who?
The number.
B. B is the number on top. Plug in 4. Plus C. F of B. I got it. I still need who? Yeah, plug it in, plug it in. What's going to happen to the plus C's if we're subtracting two expressions that both have plus C? How many times is it going to cancel? Yeah, but how many different problems that you're solving is C going to cancel?
Infinity.
All of them. Whenever you're doing f of b minus f of a, the c's are always going to go away because both pieces have them. So do we really need to write the c? Not for definite integrals. The plus c is for the antiderivative alone, not for solving definite integrals. Now hold on. All we got to do now is, can we solve this guy? Yeah, -2 over 2 is -1, -1 minus 2 over 1, -2, -1 plus 2 is, nope, I don't know what I'm thinking. I'm writing what I'm saying instead of what I'm solving. 1! Dun 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 dun. Hey. So wait, was it really helpful for us to learn how to anti-derive? Yeah. We're answering the area question with our algebra. Go team. And some of you guys that didn't like the whole, like, hey, let's make a trapezoid, let's make a rectangle, let's make a triangle, etc. This will simplify your life. We gotta do some more.
What's like the practical application of knowing the area of the area?
One practical application, which we will see in the future, is, listen. If you know how fast something is going, and let's say it's a variable rate, which means it's not a constant rate, which makes sense, right? When you're in your car, how often are you going at a constant rate the entire time? So if you know a function to describe your velocity that's varying, you can figure out with integration how far you've gone from one time to another. Yeah, it is cool. So long story short, with varying rates, you can figure out displacements or change in quantities, which has a lot of applications in motion with velocity and position, in something as silly as at an amusement park like ticket sales. If you know how fast tickets are selling, you can tell how many people are entering the park without having to do actual like little counters and whatnot. That's probably how they approximate. Well, stadiums and like even Costco, you have a little guy doing like the at the front door, right? Stadiums, turnstiles, I bet they have like a program to go ahead and just have a up-to-date one. But if you're trying to project or predict, like with weather patterns, etc., what's going to happen, sometimes it's helpful to know the rate of change, like how quickly something is occurring, and then you can figure out approximately how many will be there. So it's more of kind of like predicting, but. Question. For the next example, let's call him number 2 since we just had example number 1 in a way. We'll call him number 3. For example number 2, what's our first step? Double check your group, give them a pat in the back, make sure they're tracking. Sorry, I can't see eyes from the back of you. Okay. Well, we have 5 minutes. Let's go. What's the first step? Antiderivative. What is the antiderivative of 2 cosine x? It's not negative.
Y'all
Struggle. Do I need to put the plus C?
No.
No. No ocean today. Now what?
Misty just made a dad joke.
That's what I saw online. I just stole it.
No, that's you made a total joke.
You won't understand the actual funny one. Never mind. We'll do the houseboat joke another day. Question. What do we do next?
Plug in.
F of who goes first?
Pi.
Pi minus F of B minus F of
Something.
A. Question. Why is there no plus C?
Because
Because
they
they
cancel
cancel
out
out.
anyway.
It's a definite integral. They cancel out anyways. Who wants to write more work than they have to? Not us. Oh my goodness! I wasn't lying when I said you still have to know your unit circle and made it a grammar card. Question. What's the sign of 0? 0. What's the sign of pi? 0, because sign is the y. So we have 2 times 0 minus 0. Yay. Dun, 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 dun. Question, hold on real quickly. 2 cosine x is a cosine curve that has gone up 2, down 2. And if we have pi, he's right here. Question, does it make sense that the integral from 0 to pi would be 0? Because area above is what kind of sign? And area below is what kind of sign?
Negative.
And these are symmetric, odd symmetry, they cancel out. Hey, that was a homework question. Number 3, what are you going to do when you solve? Anti-derived, but let's not do it right away, that'd be hard. Let's rewrite 0 to 2 of, can we track if I say x to the 3/2 plus x to the 1/2? Because when you multiply x to the 1 times x to the 1/2, isn't that 1 1/2, 3/2, and then x to the 1/2? Then we have to anti-derive, so we get x to the minus 1. Nope, that's not right. That's a derivative, kind of. What do we do when we integrate? Good. 5/2, 2/5, careful, we gotta keep it straight, plus 2/3 x to the 3/2, you guys tracking? From 0 to 2. Make it easier on your brains, you crazies. Can't we make this 2/5 x to the 2.5? Plus 2/3 x to the 1.5? Think about 5/2. Change it to a mixed number. Isn't that 2.5 or x squared times x squared rooted? It makes it easier on your brain, because now when you go to plug in, you're going to have 2/5 times 5 squared, square root of 5, plus 2/3 5 square root of 5.
It's 2.
Oh, I just randomly plugging in the wrong number. Yep. Okay, let's hold on. Do you see how plugging in is going to be a little bit messy?
Yeah.
So, can this get a little tricky? Yes. Number 1, you have to remember how to anti-derive. And number 2, you have to be very careful when plugging in and simplifying, because it could get a little messy. And you might spend all this time plugging in f of b and forget, stink, what do we still have to plug in? F of a. So you're going to have to be careful of your arithmetic, but I trust that you guys can do it. You just have to take it one step at a time. Kiddos, we are not done. We got some more to learn tomorrow, but this is the main idea of section 4.4. But we have to talk about some funny things that might happen. Which means we might not finish this stink until Friday. But we'll see. We're going to keep on working tomorrow. Kiddos, start on your homework. You got to practice these definite integrals. I'll see you later. Bye.